Orthogonal matrices. We have talked about orthogonal set. Now let's talk about orthogonal matrices. Q, an n by n matrix. We say it is an orthogonal matrix if the column vectors of Q, Q1 to Qn, is an orthonormal basis for Rn. This means in particular that all the column vectors have unit norm, they are unit vector, and every two vectors are orthogonal. So whenever we have an orthonormal basis and we use these vectors to form a matrix, the matrix is called orthogonal matrix. Earlier we have seen that if that's the case, the column vectors form an orthonormal set if and only if Q transpose Q is the identity matrix. Let's go over this property for the case n is 3. Q has 3 column vectors, and we multiply Q transpose Q, we form the product. Here's Q and here's Q transpose. The 1 entry will be Q1 transpose Q1. So we put Q1 transpose Q1 here. Q1 transpose is a row vector and Q1 is a column vector. The Q1 transpose Q1 is a scalar here. And for the 2 entry, it's Q2 transpose Q2, Q3 transpose Q3. So it's here. So we see it on the diagonal. These are the norm square of the column vectors. How about off-diagonal entries? For 2, 1, we get Q2 transpose Q1. The dot product of a Q2 and the Q1 and the 3, 1 entry is Q3 transpose Q1. The dot product of Q3 and Q1. And similarly for all the off-diagonal entries, they are the dot product of 2 different vectors. Now Q transpose Q equal to identity matrix would be the same as this matrix equal to the identity matrix. And this in particular means that all these Q vectors are unit vector. And also, the dot product between every 2 column vectors are 0. So they are orthogonal. So, Q transpose Q is the identity matrix if and only if all the column vectors are unit vector. And every 2 vectors are orthogonal, which means the Q vectors form an orthonormal set, an orthonormal basis for R3. Let's see some more properties of orthogonal matrices. Suppose Q is n by n is orthogonal. Would Q be invertible? Well, the column vectors of Q form a basis for Rn, so of course, it is invertible, yes. But Q is not just an arbitrary invertible matrix. Its column vectors form an orthonormal basis. Does this make any difference? Well, Q is orthogonal, so Q transpose Q is the identity matrix. So can we see what the inverse is directly? Indeed, Q inverse is simply Q transpose. So when Q is an orthogonal matrix, it's so much easier to find its inverse. We don't need to do any operation, do any computation. We simply take the transpose of Q and we get its inverse. It's so much easier. Now suppose I tell you Q inverse, if I have a matrix whose inverse is its transpose. Does it imply Q is orthogonal? If Q inverse is Q transpose, that will mean Q transpose Q is the identity matrix. So indeed, it implies Q is orthogonal. When Q is an orthogonal matrix, there is some special property about dot product. The dot product of QU, QV is related to the dot product U transpose V in a very simple way. Let's work out the dot product on the left-hand side. We get U transpose QV. And what does this mean? Q transpose Q is the identity matrix because Q is orthogonal. So this means this is equal and this is equal. So when Q is an orthogonal matrix, dot product is preserved. If we have dot product, U transpose V, and if we first have QU and a QV, then the dot product is still the same. In this case, we say the dot product is preserved. In this property, we see that whenever Q is orthogonal, dot product is preserved. Now let's ask the converse. Suppose dot product is preserved. We are given a matrix Q, and this Q matrix preserved the dot product. QU transpose QV is the same as U transpose V, and this is true for all UV vectors in Rn. Does this imply Q is orthogonal? Well, this is true for all UV vectors, right? And to see if Q is orthogonal, we need to check its column vectors. So let's try to choose some UV which will reveal its column vectors. Let's choose U to be the ith standard vector and V to be the jth standard vector. Then we know the products QV will extract the jth column vector of Q. So on the left-hand side, we get QEI transpose QEJ. And this is the same as QEI is the ith column vector, QEJ is the jth column vector. Dot product is preserved, so on this right-hand side, what we get is the dot product of EI and EJ. And these EI, EJ vectors, we know they are orthogonal, they are orthonormal. So each one of them is a unit vector, and every two are orthogonal. And that means each QI vector is a unit vector, and every IJ vector are orthogonal. Now, if Q is orthogonal, does that mean it preserves norm? That means the norm of QU, the same as the norm of U for all U. Is this true? Can we use the third property in this case? And that's the case, right? If we can just choose V to be the same as U, then we get this property. Now let's ask the converse. Suppose Q is a matrix, n by n matrix that preserves norm for all U vectors in Rn. Does that mean Q is orthogonal? Then it's the same as asking if all the vectors of Q are unit vector and if every two vectors of Q are orthogonal. The first one is easy to answer because it preserves norm. So if we just choose U to be the ith standard vector, then on the left-hand side, we get the ith column vector of Q, and on the right-hand side, we get EI norm, which is equal to 1. So all the column vectors of Q have unit norm. Now let's think about the orthogonality among the vectors. We want to see if the column vectors of Q are orthogonal. Orthogonality between two vectors means that we need to somehow cook up dot product. But the only thing that we know is this property. So we need to choose U so that we can somehow see dot product between two column vectors of Q. So let's try U, that is the sum of the ith and jth column vector, jth standard vector. So by the given property, we know the norm square of U is the norm square of QU. This will be the same as the sum, the norm square of the sum QI plus QJ. And this is the same as QI norm square plus QJ norm square. And here we got the dot product. The left-hand side, EI plus EJ, has norm square equal to 2. And on the right-hand side, because we already know Q is a unit vector, QJ a unit vector, so this is 1, 1, we get 2, and then the dot product. And we see what the value of the dot product is. It's equal to 0, isn't it? Whenever I is not the same as J. So the converse is also true. If a matrix preserves norm, then it is orthogonal. And combining this property and this property, we can see that it's an if and only if condition. A matrix is orthogonal if and only if it preserves norm. Summarizing what we have just talked about, we have theorem 6.9. Q is n by n matrix. The followings are equivalent. Q is orthogonal if and only if Q transpose Q is the identity matrix. Q is invertible and Q inverse is its transpose. It preserves the product and it preserves norm. These are all if and only if conditions.